Hello, what's going on? Question 3, SAC 1. This is about biogas. Now, methane can be considered as a biogas as well as a natural gas. It depends on how you source it. Okay, all right. This process is essential for various industrial application. Okay, whatever. Okay, write a complete balance equation for complete combustion of methane, which is quite easy. Interestingly, they are not asking you to do a thermochemical equation. They are just asking you to do a balanced chemical equation. In this case, what do we have to do? Get the pen, again red, okay. Then methane, room temperature, which is a gas, reacting with oxygen. Everyone knows this reaction. Complete combustion, so you are going to get carbon dioxide gas, not carbon monoxide, that is incomplete, isn't it? All right, carbon dioxide gas and plus H₂O is the liquid. And make sure you balance it. Combustion of methane or methane gas. So water can be liquid or gas. That is fine. So what do you need to do next to balance this? In order to balance this, you put 2 here, 2, 2, 2. All right, I think we can get that 1 mark easily. All right, let's look at the part B. What is part B saying? Given that 50-liter gas cylinder was filled with 75% of the way with pure methane. All right, you have 50-liter gas, 50-liter cylinder. In that, you have 75% of the cylinder is pure methane. All right, the question is asking you to calculate the amount of energy released by the complete combustion of entire gas cylinder in megajoules. Okay, 2 marks. All right, firstly, you need to find out the volume of the methane. Okay. Volume of the methane, SLC condition. Yeah, I was looking for the condition. I nearly missed the condition. Right, find out the volume of the methane. So what is the volume of the methane? Volume of CH4 is not 50. Why it is not 50? It's at 75%. So you need to work out what? Out of that 50 liter, so 50 times 75 over 100, that is the amount of liters of methane you have. So that's the amount of liters. All right, at the SLC condition, then you can find out the number of moles of methane, because at the end of the day we are going to use a chemical formula to find the energy. What is the formula that we are going to use? Remember, Q is equal to delta H times N from the data booklet. Delta H is, you get the delta H from the data booklet. That is what I was meant to say. All right, so find the number of moles of methane. What do you need? What do you need to do? You need to divide the volume, which is the over Vm. Everyone knows what Vm is at SLC. Every mole of a gas will take 24.8 liters. So if you want to find out the number of moles of a gas, only for a gas, not for a liquid, only for a gas, you divide V volume by 24.8. In this case, I'm going to use that. What's that? Which is what? I'll do it here. What is V? That is V is 50 times 75. And Vm is 24.8. I hope you will understand this. 24.8. That will give you the number of moles of the methane, which is going to be 1.512 moles. That's the number of moles. Now we got the number of moles of methane, which is the fuel, isn't it? So if you know the number of moles of the fuel, in order to find the delta, in order to find the energy, you use this formula. Q methane is equal to delta H of methane from the data booklet times number of moles of methane which we've got. All right, now let's do this. Delta H is going to be, I think from the data booklet, is it 890 minus 890 times, now remember this is delta H is in kilojoules per mole, so the Q, this value is in kilojoules, so number of moles which is 1.512, then you get the answer minus 1345.77 kilojoules. Now don't leave the answer in minus, because energy is released, therefore we say 1345. I'm going to move this up. 1345.77 kilojoules are released. Now the question is asking you to find the megajoules. To convert kilojoules into megajoules, you need to divide it by 1000, right? Do you remember 1000? Some people forget to do this division, and they ask me, hey sir, how do you convert kilojoules to megajoules? I see the data booklet as well. Divided by 1000, how many significant figures? Two significant figures. It is 1.3. It's two significant figures. Well, okay, just 1.3 megajoules. 1.3 megajoules. Okay, that part is done. That's not difficult, is it? All right. Now we are going to do the next question. Now next question, look at this question. All right, the question says, what does it say? Methane can be converted into hydrogen. Oh, we are producing hydrogen. Oh, that is one way of producing hydrogen. This is called steam reformation. Is this the renewable hydrogen that we are making? Are we making this hydrogen renewable? I was meant to say the hydrogen we are making, is it renewable or not? Oh, yes. It depends on how methane is sourced. If the methane is a natural gas, if the methane is a natural gas which is non-renewable, therefore the hydrogen you are producing is non-renewable as well. So that hydrogen is not renewable. However though, if the methane comes as a biogas, if this is a biogas, the hydrogen you are producing is going to be renewable hydrogen. That is one way. This is a one way of producing renewable hydrogen using biogas, and we send the biogas, we react the biogas with steam, then you get hydrogen and carbon monoxide. So this is renewable hydrogen. All right, your teacher can make a SAC question based on this reaction, steam reformation. You don't have to memorize it. No, you don't have to memorize that. All right. Okay, now that's not the question. Okay, this is some additional information for your future SACs. The question is asking you, suggest a potential danger of undertaking steam reforming in a sealed and pressurized container. So what they are saying is, you are doing this reaction in a sealed container. Potential danger. To understand that, to understand the potential danger, we need to look at this reaction. As you could see, all the reactants and products are gases. Look at this. Methane is a gas, water, steam is a gas, hydrogen is a gas, carbon monoxide is a gas. Now you are starting with, look, 1 mole of methane and let's say 1 mole of steam, which is also water, which is also a gas. Obviously at the beginning you got 0 and 0 of this. Now look what happens. So you are doing this reaction in a sealed container. Now according to this reaction, you are using 2 moles of gas. 2 moles of gas you are using, and you are making 4 moles of gas. How did I end up getting 4 moles? Look at that. You are starting with 2 moles, then you are making 3 moles of hydrogen and 1 mole of carbon monoxide. So at the beginning 2 moles, you make it 4. 2 becomes 4. You are increasing the number of particles inside the vessels. Not inside the vessel. Inside this container. It's a sealed container. Suddenly you are increasing the number of gas particle. What will happen when you do that? The pressure will increase suddenly. Pressure suddenly will increase because 2 becomes 4. Pressure suddenly will increase. Then what will happen? Boom! Rupture. Because gases can rupture a sealed container because this sudden increase in pressure can make the cylinder part dangerous. Okay, I will write a proper answer in the description like I have like what I have done previously. Now listen. So this is the clue. 2 moles become 4 moles and suddenly the pressure increases. That is what you need to remember. 2 moles become 4 moles and suddenly what? Pressure increases. Okay. Now let's look at the next question. Let me get the next one. Okay. Now the next question is asking you, use your response from part C1 to explain whether the same danger would still present all the reactant and product are liquid. Okay. Now in this case, they are saying, hey, if all these reactant and the products assume that they were liquid, would this still a problem? I was meant to say, when you have all these reactant and product liquid, will still there be a danger doing this reaction in a sealed container? Now listen, what happens? You are starting with, this case, 2 moles of liquid and you are converting into 4 moles of liquid. Now this is liquid, not gases. Okay, even though there is a change in number of moles, or change in number of moles is the same, but previously they were gases. Gases can expand. Do you think liquid can expand? A very small liquid cannot expand the way the gas expands. So in other words, liquids are not expandable. So there is no change in volume. So there is no danger. Is that clear? Right, I'll write the answer for that in the description as well. Okay? The last part of the question 3. Now this is a 3-mark question based on a calculation. But this question involves a lot of concept. Okay? Therefore, instead of doing that, let me change the question for the time being, and we will do the changed version of the question first. Then we'll go back and do the actual question. Is that okay? Right? I think that is the best way. So it is going to be less stress for you. That is why I wanted to make a small change. All right. The small change I'm going to make is this. Now, okay, let me read it out. The hydrogen gas produced through the steam reforming was combusted and found to have released 1.5 megajoules. So remember, during the steam reformation reaction, we are producing hydrogen. So they have combusted that hydrogen, and they have produced 1.5 megajoules of energy. Okay, energy in a setup. Okay, full stop. I'm going to cross this out. So I'm going to say there is no heat lost. In other words, all the energy that the hydrogen released has been absorbed or has been measured, which is going to be 1.5 megajoules. Now the question is asking you calculate the amount of methane gas required to produce that amount of hydrogen gas. So firstly, now this energy, what energy? Okay. This energy was released due to the burning of the hydrogen. Is that clear? Now what do we need to do? If we can find out the number of moles of hydrogen that is responsible for making this amount of energy, then we can use stoic and we can find out the number of moles of methane and the volume in SLC. All right, that's our plan. So let's try to find out the number of moles of hydrogen that makes 1.5 megajoules of energy. Okay, so number of moles and the energy, do you know the formula or the ratios? You can use the formula from the data booklet or the ratios what I've told you. Not told you, but I've taught you. All right, this time I'm going to use the formula delta H, in this case hydrogen, is equal to what? CH₄, energy of the hydrogen, divided by the number of moles of the hydrogen. Now I normally use the coefficient, but coefficient is 1 if you are going to use the formula, if you are going to use the delta H value from the data booklet, right? Because coefficient matters if you are given a thermochemical equation. Now in this case there is no thermochemical equation, so we just can use the formula from the data booklet. Okay, now you need to find the number of moles of hydrogen is what we are after, which is going to be equal to Q hydrogen. Q hydrogen means energy released by hydrogen and divided by the delta H of hydrogen. Now Q hydrogen is 1.5 megajoules. You need to convert into kilojoules, because delta H in the data booklet is given to you in kilojoules per mole. All right, so this is minus 1.5 times 10 to the power 3 kilojoules divided by What's the delta H value of 286, which is minus as well? So minus minus cancel out, you get the answer, number of moles of hydrogen, which is, let me use a calculator because I haven't got that value. Where's stupid calculator? Oh no, it's opening. Okay, sorry. So 1500 divided by 286 is the what? Which is 5.244 moles. Which is 54425. How many significant figures? 2 significant figures. So let me use the answer for 5.2 moles of hydrogen. Now we got the 5.2 moles of hydrogen. Now if you can remember this equation. Okay, let me write the equation here as well. Okay, steam reforming, right? Methane plus H₂O, they are all gases. You are going to produce, it's a equilibrium reaction, I guess. Gas, don't worry about the equilibrium, gas, it is hydrogen and CO. Okay, why are you balancing it again? I don't know, I shouldn't have had that equation written before, but that's okay, that's okay. In this case, okay, what? No, it's 3, yeah. It's 3. What are you doing? What are you doing, sir? It is 3. Let me get it clear, okay? Otherwise, it has to be 3. Alright, so this is 3. Now, see the ratio. Now, we got the number of moles of hydrogen. Therefore, number of moles of methane, what you need to do? Ratio is 1 to 3. So 5.2 divided by 3, which is 1 point, what? No. 1 point, no, I use a calculator, man. Divided by 3, which is going to be 1.7, 1.74. 1.74 moles of methane. Methane is a gas. The question is asking you calculate the amount of methane in liters. So we need to find the volume of methane at SLC. You know that. You know that how to do that, which is what? Number of moles of methane, which we have found, times by the 24. Again you made a mistake. 24.8. No wonder I'm making mistake. It is 1:30 is the time. Okay. Times 24.8, right? So put those numbers into a calculator, which is 1.74 times 24.8, which is what? 24.8. I will go for 43 liters. 43 liters of methane you require. Now we are going to do the actual question. Now what's the difference between this question or changed version of the question and the actual question? Okay, now we did this calculation assuming that there is no heat loss. There is no heat loss. All the heat that the hydrogen released or hydrogen has released, all the energy the hydrogen has released has been captured so that we could measure. So we were able to capture all that energy the hydrogen released. And that is the assumption in this question. In other words, there is no heat loss. All the energy the hydrogen released was measured. We could capture it, we could measure it. Is that clear? Now, this question is a bit different. Okay, let's go to the actual question. Okay, so let me erase this one. Where's eraser? Okay. Eraser is not working today. Why is not eraser working? Okay, let's say eraser. Ah, eraser. Eraser is not working, eraser. What is this eraser? Ah, it's working now. All right. Now let's clean all the board. Man, you know, when I was your age, we only had black boards. Now this is a digital board. Man. All right. Now listen. Okay, let's do this question again. Okay, now the same question, but the difference is it says 20% of the heat is lost. What do you mean by lost, sir? You remember we burn hydrogen and we measure the amount of heat the hydrogen releases. That is what we were meant to do. During the measuring process, we have measured 1.5. However, though, after 24% of heat lost. In other words, during this process, we were able to capture, in other words, 24% heat is lost means 76% of the heat from the hydrogen has been absorbed. So this value here is the amount that we were able to capture. Now I want you to understand this very clearly. I want you to understand the fact that hydrogen ended up releasing more energy than 1.5. However, we were not able to capture that energy. Is that clear to you? Just because of heat loss, or the heat loss does not affect the chemical reaction. Hydrogen was producing that amount of energy. Only 70% of that 70% of the original amount of the energy hydrogen produced is 1.5. Is that clear? Now, to do this question, we need to find out the original amount of energy the hydrogen has released, because 76% of that, only the 76% of that original amount of energy is 1.5. So firstly, we need to work out what is the original amount is. Now let me give you try to explain it different. Let me try to explain it using example. Okay, let's put it this way. You have a 2-liter bucket. Okay, the bucket. What is this? This is a bucket. Okay, let's say you have a bucket. You can put 10 liters of water. All right, so when the bucket is full, you have 10 liters. Now let's say there are holes in the bucket. Due to these holes, only 75% of the water is going to be left in the bucket, right? And 25% is going to be lost. So if you put 10 liters, only 75% of that is the one that is going to be left in the bucket. 25 is going to be lost. Okay, let me say 100 liters, so it's easy. It's 100 liters. Okay, 100 liters. Now let's say in a situation, okay, let's say that you keep on pouring water into the bucket, keep on pouring water into the bucket. At one point you will see that there is 75% liters. 75% liters in the bucket. At this point, you have 75% liters of water at one particular point. To store or to have 75% of liters left in this bucket, what is the amount of liters of water you have poured in? It is 100, isn't it? So you need to pour more. Then there will be some of the water will be lost, but there will be some water left in the bucket. The point I'm trying to make is this: 75 liters is the only amount that we could capture, even though you poured 100 liters, right? This is exactly similar to what the question is saying. 25% of the heat is lost, therefore 76% of the heat is absorbed, so that we could measure that amount of heat that got absorbed. So 76% is 1.5 megajoules. That is the amount that we could capture. Now we need to find out the original amount of the heat the hydrogen released. So how do we do that? Now we have to do simple ratio stuff. Okay, so let me do this. Let me write a statement. 76%, okay, 76% of the original amount of energy, original amount of energy, 76% of the original amount of energy of hydrogen, two F's together, and original amount of energy from hydrogen is 1.5. Okay, let me clear that. Is 1.5 megajoules. Okay, this is the 76%. Now what we need to do, therefore Q hydrogen, we say original. Now this is the Q hydrogen, not original, this is we say Q hydrogen after heat loss, after heat loss. Okay, so now we need to find the Q hydrogen original amount. Okay, to do that, what do you need to do? Now, so original value should be a higher value than 1.5. Therefore, to find the original value, how do you get a higher value? You need to divide it by 76 times by 100. Because if you do the other way around, you get a lower number. Now you need to know that the original is the higher value. Is that clear? Therefore, so we get this value. What's that value? Okay, we need to convert into the megajoules. This is going to be in megajoules, which is going to be 1.97 megajoules. Let me convert into kilojoules. 197 1970. This is the kilojoules. So that's the original amount of the energy that hydrogen has released. 1970 kilojoules, not 1500 kilojoules. In this case, that is 76% of that. Now we can do the question. So that's then find the number of moles of hydrogen. To do that, Q hydrogen divided by what? Delta H of hydrogen, which is minus 1970 divided by, okay, delta H of hydrogen is, do you remember the delta H? 286 minus, that will give you, what's the number of moles? 2.30 moles. So two significant figures, 2.3 moles, 2.0 moles, because that's, even though this is two significant figures, whatever the answers that you get in between, make it for three significant figures. So that is 2.30 moles of hydrogen. Therefore, number of moles of methane, you divide it by 3, but the ratio is what? 1 to 3. Number of moles of hydrogen divided by 3, which is going to be, no, I made a mistake there, didn't I? No, this should be, this is wrong. I was looking at the paper, which is 6.9. 6.9 moles. My mistake, sorry about that. This is 6.9. So 6.9 divided by 3, which is 2.3 moles. That's the number of moles of methane, 2.3. Then find the volume of a methane like the way we found last time, 2.3 times 24.8. The answer is going to be 57 liters. 57 liters. So that's a good question. All right. Now we finished 3 questions here. Question 4, I don't think we can do that because we are not going to look at calorimetry. So I'm going to get a new question from another SAC. All right. Thank you for listening. Talk to you soon. Love you for loving chemistry. See you. Bye.